We constantly guess what the future will look like, but we rarely ask how it will be funded. Let's run the numbers. Specifically, we examine the economics of commercial fusion energy abundance. If energy became economically free, we might assume that all scarcity would disappear. However, this assumption ignores the physical constraints of raw materials, manufacturing capacity, and land availability. Under this assumption, free energy makes processing cheaper, but it does not create resource inputs. Copper, lithium, and rare earth minerals remain finite physical elements in the Earth's crust. This mismatch creates an immediate economic bottleneck. When one major cost input falls to zero, demand for complementary inputs rises exponentially, causing their prices to skyrocket in global markets. We must analyze how incentives shift when the limiting factor of production changes. The abundance of electricity does not eliminate scarcity. It merely relocates it to the next binding constraint. So, how does an economy function when energy is free but everything else is expensive? The answer lies in the Jevons paradox, where efficiency gains increase resource consumption pressure. As fusion reactors begin to supply unlimited grid power, we observe the binding scarcity. The bottleneck shifts from energy generation to the raw materials needed to transmit and utilize that power. When electricity costs nothing, the incentive to build massive industrial systems increases. However, the physical copper needed for grid distribution and motors remains highly scarce and expensive to mine. Here is the constraint: we cannot scale electric infrastructure without massive physical inputs. The scarcity of these materials sets a hard limit on the actual adoption rate of fusion technology. The observable consequence is a dramatic price spike in industrial metals. While energy bills drop to zero, the capital cost of machinery, vehicles, and grid connections rises to historic levels. It comes down to scarcity. Free energy makes extraction cheaper, but it also increases the rate of resource depletion, accelerating shortages in metals, fresh water, and high-purity silicon reserves. This shifting bottleneck alters the balance of industrial power. Nations with rich mineral deposits capture the economic value of fusion, while energy-rich but resource-poor regions face severe structural constraints. To analyze this scenario, we must define the Jevons paradox. Historically, when technological progress increases the efficiency of a resource, the cost of using that resource falls dramatically. This price reduction increases the quantity demanded, which frequently offsets any savings. Instead of consuming less of the input, the overall system consumes far more in total volume. Interestingly, this principle applies to energy abundance. When fusion makes electricity virtually free, we do not simply use the same amount of power. We expand our energy-intensive activities exponentially. We begin to desalinate oceans, refine lower-grade ores, and run massive computation centers. Under this assumption, our total demand for energy increases until other physical limits are reached. The key distinction is that while energy can be generated cleanly, the physical infrastructure to capture, convert, and store that energy cannot be expanded without serious ecological and material costs. For example, manufacturing millions of fusion-compatible magnets requires vast amounts of niobium and helium. These elements are non-renewable, and their extraction creates significant environmental and economic externalities indeed. For instance, instead of sorting waste manually, recyclers will use massive energy-intensive thermal processors to melt and separate materials, substituting cheap power for labor in the warehouse facility. These cartels restrict the supply of critical metals, artificially raising prices to maximize their national revenue. Resource-poor nations find themselves dependent on these cartels, creating geopolitical instability over time. The core mechanism of this transition begins with the supply curve of fusion power. Because fusion fuel is abundant, the marginal cost of generating electricity drops close to zero. This shift moves the energy supply curve outward, creating a massive consumer surplus. Businesses and households respond by substituting energy for other, more expensive inputs wherever physically possible. Follow the incentive structure. If electricity is free, companies will choose to run energy-inefficient processes if they save on expensive labor or specialized capital equipment during production cycles. This substitution increases the demand for raw scrap metal and processing catalysts. As multiple industries automate and electrify, they all compete for the same limited pool of physical catalysts, raising prices. These cartels restrict the supply of critical metals, artificially raising prices to maximize their national revenue. Resource-poor nations find themselves dependent on these cartels, creating geopolitical instability worldwide. Furthermore, the environmental cost of mining intensifies. Using free energy to mine lower-grade ores requires displacing vast amounts of earth, leading to local landscape destruction and severe water contamination issues. This environmental damage triggers regulatory pushback and community resistance, creating legal bottlenecks. Projects are delayed and the cost of environmental compliance rises, creating a new form of resource scarcity. This institutional scarcity limits the rate of industrial expansion. The abundance of energy cannot bypass the democratic, legal, and regulatory processes that govern the use of physical land structures. To evaluate this model, we must establish its boundaries. Under this assumption, the migration of scarcity only occurs if the manufacturing of fusion reactors itself does not become a bottleneck. For instance, if reactor construction requires highly specialized, non-scalable expertise, energy abundance would be limited. In this case, energy remains expensive, and the Jevons paradox does not materialize. Additionally, an alternative equilibrium could emerge if resource substitution technology advances rapidly. If engineers find ways to replace copper with abundant carbon nanotubes, material scarcity would be temporarily averted. However, this substitution assumes that carbon nanotube production does not create its own scarce input requirement. In practice, every technical solution introduces a new set of material dependencies. We must also note the geographic limitations of land use. Even with free energy, locating fusion reactors and industrial sites requires flat land close to major consumption centers. This physical boundary means urban land values will rise, offsetting energy savings. In models where land is private, landlords capture the economic surplus generated by the free energy technology. A validating case is found in the history of agricultural mechanization. Tractor adoption eliminated horse labor but shifted scarcity to fossil fuels and arable land, transforming farm economics permanently. This brings us back to our opening question of what becomes the new oil. The answer is that raw mineral deposits and manufacturing capacity replace energy as the primary strategic assets. The consequence of this shift is a reorganization of global trade. Industrial dominance is no longer determined by energy access, but by control over the mineral supply chain. Change the assumption, change the equilibrium. If we establish a circular economy with near-perfect recycling, we could theoretically decouple industrial production from raw material extraction constraints in this scenario. Under this assumption, free energy is used to power automated recycling systems that recover every atom of metal. This would stabilize material prices and prevent resource depletion over time. However, achieving perfect recycling requires high capital investment and faces thermodynamic limits. We cannot recycle materials indefinitely without some loss, meaning raw input demand never falls to zero. Until recycling technology reaches that level, the material constraint remains binding. The practical resolution is that energy abundance will intensify rather than resolve our resource allocation conflicts indeed. This reality forces us to reevaluate the promise of fusion power. The technology does not lead to post-scarcity, it merely changes the nature of what we must ration. By recognizing this bottleneck, we can avoid the mistake of assuming energy solves all problems. True sustainability requires managing our physical resources alongside our energy generation capacity properly. The core mechanism of this transition begins with the supply curve of fusion power. Because fusion fuel is abundant, the marginal cost of generating electricity drops close to zero. This shift moves the energy supply curve outward, creating a massive consumer surplus. Businesses and households respond by substituting energy for other, more expensive inputs wherever physically possible. Follow the incentive structure. If electricity is free, companies will choose to run energy-inefficient processes if they save on expensive labor or specialized capital equipment during production cycles. The resulting supply chain disruptions cause high price volatility in commodity markets. Manufacturers cannot project production costs, leading to reduced long-term investment in new factories and infrastructure always. Change the assumption, change the equilibrium. If we establish a circular economy with near-perfect recycling, we could theoretically decouple industrial production from raw material extraction constraints in this scenario indeed. Under this assumption, free energy is used to power automated recycling systems that recover every atom of metal. This would stabilize material prices and prevent resource depletion over time. By recognizing this bottleneck, we can avoid the mistake of assuming energy solves all problems. True sustainability requires managing our physical resources alongside our energy generation capacity always. Ultimately, physical reality is governed by conservation laws. Any attempt to expand industrial activity using free energy will tend to collide with the finite limits of our planet. In practice, when evaluating future energy projects, we must look beyond generation capacity. We must inspect the entire material supply chain required to utilize the power. If a proposal lacks a clear strategy for sourcing copper and magnets, it is likely to face high capital costs, regardless of the electricity price. We should analyze energy abundance scenarios by testing which raw materials face the greatest demand pressure. This helps identify the true winners of the transition. Another application is to invest in material substitution research. Developing alternatives to scarce minerals is a necessary step to unlock the value of fusion energy. Furthermore, we must compare centralized resource allocation models with market pricing. Market prices tend to adjust faster to material shortages than administrative quotas can. We must also maintain a clear distinction between a speculative scenario and a forecast. This analysis helps us map incentives, not predict exact commodity prices. By focusing on follow the incentive structure, we can better evaluate the long-term feasibility of industrial projects, avoiding the hype of free energy promises. The critical step is to design regulatory frameworks that manage resource extraction responsibly. Only then can we prevent energy abundance from triggering ecological depletion. We must look beyond the reactor and analyze the physical materials that contain its power. The future is just incentives at scale. See you tomorrow.